All right. All right, more than meets the eye here. Okay. Come on.
More of an Autobot?
Decepticons.
It's funny that the whole movie is, I was talking with the older man that works at the power plant.
Yeah.
He said whenever he feels the transformers, just like powering.
There you go. All right. I'm trying to get this thing to go properly full screen online. You guys don't see it in the room. It looks weird. All right. Gosh. There we go. All right. Okay. So Transformers, you guys, so you've seen them before. You see them all over the place. I want to understand them a little bit here. Okay. So Faraday's law. What is Faraday's law? Who remembers Faraday's law from physics? Somebody online. Make sure to keep the online guys engaged. What is Faraday's law? Anybody remember?
Is it the amount of current going through a cross-sectional area?
No.
No, it's what's the voltage through the
It's what? Is that tone out there?
yes, sir.
Okay. What do you think it is, Tone?
It's me.
All right. Faraday's law is probably one of the most important things that's ever been developed because it is the thing that basically made it such that we were able to power society. Right? Faraday's law basically says if I take a coil, and there's an equation, there's an integral of this equals that, but in words, in fact, what it says is in words, or let's see, B dot dA by dt equals a voltage, which I don't know, it's an electric field, I guess. All right, in fact, a voltage, and I'll say E dot dL. All right, it's a crazy looking thing. The reason you don't know it is because that's probably how you know it. Is you probably, I mean, even if you haven't seen it this way, you saw in physics 2, you saw some version of this thing, right? In words, what does that mean?
It's like what the change of magnetic flux causes a current.
Change in magnetic flux induces a voltage in a coil. So if I take a coil and I put a coil inside of a changing magnetic field, there will be a voltage at its terminals. All right, that's the basic principle by which if you go to a power plant, right, and there's basically there's spinning magnets on the generators. Those spinning magnets are basically creating voltages in basically in 3 coils on that generator. Okay, and so those voltages then supply all the power to the world, right? So if I look at this guy right here, right, if I said let's put a voltage source on a coil, all right, there's going to be a current that goes into this coil, all right, current I. Now, as a result of that, there's a magnetic field that's created inside that coil, isn't there?
Yeah.
And where would that, how do I figure out where that magnetic field is?
Move around and stop all the time. It's dependent on the number of loops, right?
No, I mean, where do I figure out where the magnetic field is, right?
Based on the direction of current.
Based on the direction of the current. So if I have a wire, right, and I have a current going this way, I of T, right, where's the magnetic field going to be? How do I figure out where that is? Right-hand rule.
Right-hand
Right? So
rule.
if I put my right hand around that wire, there's going to be a magnetic field. Which way would it go? Somebody online.
Opposite of current.
Where?
The inside.
It's going to go around this guy, right? In which direction would it go? Clockwise or counterclockwise?
Top would be going out of the page.
Yeah, right. It's going to go like this. So we come out at the top and in at the bottom, right? So it would go around this guy like that. So if I had a coil like this, and I had that I of T go in the direction that I have right there, where would the magnetic field be in this coil? You get a coil. Well, it'd be around it would be wrapping around the wires, right? So in this case, where would it go? So if the current's going into the top right there, where would all the field be from this thing?
Inside the center of the coil.
Inside the center of the coil. Now they'd be
But wouldn't
closed
wouldn't
circles.
it be laughing, looping out?
It'd be, so yeah, it would go in the center of the coil and it would go around like this. Right, so it would go out and it always goes out in space and then loops back on itself like that. Magnetic field lines are always closed, right? So it would go something like that. There'd be a bunch of magnetic field in the center of it, but they would come out and they would come back in, okay? So that's how I create a changing magnetic field. So over here, right, if I take a coil and I stick a coil right here, what's going to happen to that coil?
A lot of current.
There's going to be, well, so
It's going to be voltage from.
there's going to be a
magnetic field.
voltage, right? And I like to say it that way. There's going to be a voltage because if it's open, I get an open circuit voltage there, right? I don't get a current because there's no closed path for current to flow. But I'll get a voltage, and if I stick a load on that, then there will be a current. Okay. So basically, if you think about this, it's like you have one circuit that's creating a field that's inducing something in another circuit. Okay. So you're basically, this guy is now like a voltage source, right? Thevenin equivalent wise, I can think of this thing now as there's some little voltage source inside of this thing, right? And it probably has a Thevenin equivalent. There's wire, it's got some resistance and stuff, right? So there's a little voltage source that I've created over there. And we use these all the time, right? So if I stick a coil specifically, I stick another coil over here, right? This is what I was trying to show. And I start running field through here, you're going to induce a voltage here, right? You induce a voltage at these terminals, okay? Now, if you look at this, the picture of the coil that I drew right here, right? Let me see. Be careful, I'll close up my lines carefully here, right? If you look at the way that I drew this guy here, how well, so if I've got, this is the left coil, and this is my receiving coil over here. Okay. How well am I doing at directing the magnetic field into that coil? Not well, not very well at all, right? If my job is to basically direct the magnetic field into the coil over there, I haven't done a very good job. What I probably want to do is direct that field to go from the coil where I'm putting it in to the coil where it's coming out, right? So what would be a good way to do that? Maybe. Even if I put the two coils on top of each other, which you could do, it still would have a fair amount of what I call leakage, where some of the field wouldn't couple into the other one. So I use this term coupling. I want the field from one to couple into the other one, pass through the other.
Increase the magnetic.
Not increase it. What I can do, so if you've ever seen a real transformer, do you ever have two coils just sitting there in space? If you've seen a real transformer, what do you have when you have a real transformer?
You have a core. You have an iron core to carry the magnetic field around into the other coil.
Yeah, you have an iron core that carries it around, right? So it used to be back in the old days, you actually would learn about what they call magnetic circuits, right? Which is to say what I do is I put a voltage source on what I call a primary winding. Okay. So a primary winding over here, I put a voltage source on that primary winding. And that's going to cause a current to go in, like I've shown the direction of this guy here, right? So VP, V primary, and then IP, I primary. And then over here, I got another coil that's open circuited, all right? So looking at that, basically, so I do the right-hand rule to figure out the direction of that magnetic field. What this iron, or what we call in physics terms, high mu material, what that does is it directs that magnetic field. And oftentimes we say magnetic flux. What's flux and how is that different than field? What is flux? Unfortunately, you guys just know equations. You don't know the details, right? What's flux mean?
It's the rate of change. I'm thinking L3.
Isn't it the flow of electrons?
So flux is how much field goes through an area, right? So if there's a cross-sectional area A to that core, flux is how much field is going through it. The total amount of field lines. If I counted the field lines going through that would be the flux. Okay. So what happens when the reason they have that big hunk of iron, they do. If you go next to a transformer, if it's a big transformer, many of them are, right? What you see, like in your neighborhood, you probably, like my neighborhood, if I walk around my neighborhood, there's a bunch of 25 kVA transformers, right? That's meant for one for every 5 houses, basically. We'll talk about why that is, but there's basically one transformer for every 5 houses. And it's a big green box. If you open that green box up, what you're going to have inside of there is iron like this. And what that iron is doing is it's directing the field that's created by the primary over to the secondary. And it's inducing a voltage over there. Okay. So the way I think of it is that iron is like a pipe. It's like a conduit that's directing the magnetic field over. So I wanted to set up a demo, but it's hard to figure out how to set up a demo with the Zoom thing. But basically, if I take 2 coils and put them on top of each other and put a voltage on one of the coils, and if they had the exact same number of turns, you would think that they would probably have the same voltage, right? They don't unless I really make sure that I have this iron there, right? One thing to think about iron is expensive, iron is heavy, right? So the only reason I use this thing is because it directs the field to where it needs to go, right? And that's
the definition of flux, right? What was the definition?
Definition of flux is how much field I have in an area. So if that iron that I have shown there has an area A, cross-sectional area A, the flux is the total amount of field that's going through that thing, okay? And it's the total amount of field that we care about because it's the total amount of field that goes through the coil on the secondary side that creates the voltage, okay? And ideally, I want all of the flux that came through the coil on the primary to go through the coil on the secondary. Ideally, all of it goes through. If it doesn't, Duke's losing out, right? The utility loses out on that if they don't. They want all of it to make it from one side to the other. Now, these guys come up a lot in power systems. We're going to start talking about power next week, right? But I wanted to kind of start. This guy's a useful thing anytime we talk about power is to be able to understand the transformer. It's just a circuit element, right? I don't need to know anything about power per se here. It's just a circuit element as far as we're concerned. Okay.
So
Tyler.
iron's so heavy and all that, why don't we use a different high MU material?
So the question he asked was, why do we use iron if it's so heavy and expensive and all that sort of stuff? It's iron-based materials. So ferrites or ferromagnetic materials, they're called, are really the only type of material that has that high mu capability. There's ways to make transformers smaller. That would mean changing the frequency of the power system to a much higher value. Okay, and so mobile power systems like in vehicles or ships, they will do that. They'll run with aircraft, they have a 400 hertz power system, which means makes things smaller and things like that. But that's kind of outside of our scope here. Okay.
So I have another physics question, and so it's going back to the loops. Isn't there also a way, like, instead of using iron, what you could do is you take the secondary and rotate it over its horizontal axis over the primary coil to try and get more field? Or like, is that something that would work? Or am I remembering?
No. I would have to I could take the secondary coil and put it directly over top of the primary coil, and that would have pretty good coupling. But I really need to have the iron to make sure that none of it leaks out. So what I'm doing here is I'm trying to direct all of it to go from the primary into the secondary.
Right, but what I'm saying is, maybe I didn't get this across, is like if you put the secondary on a crank and so, you're constantly, kind of changing it and rotating it over top of that field.
That wouldn't work too well because I see where you're going with that, but you want to make sure at every instant you're capturing it all, basically.
Right.
Yeah. Okay. All right. So the basic physics kind of makes sense. I have this iron piece. So I'm moving voltage from one side to the next. The number of turns controls how much voltage I get on one side. Yeah, Christian.
You said that the iron will direct most of the magnetic field. Is there a little bit of it that doesn't get caught?
There's a little bit, the way I think about this thing here, this iron is it's just like wire, right? you guys make the assumption that all of the electrons that leave a voltage source make it to the resistor and then back into the voltage source when you think of a circuit.
In an ideal world.
It's an ideal world. Some of the electrons leave the wire and actually go off elsewhere. It's a small number of them because copper is really darn good at making sure that those electrons get to their destination. High mu materials like iron are really good at making sure the magnetic field gets to its location, right? That's why we use it, right? It's just like copper in an electric circuit. In an electric circuit, copper gets the electrons to the load. In a magnetic material like iron gets the flux or the field over to its source or to its destination, which in this case is the secondary. Okay, that's the ideal. It's not as good at delivering the flux as copper is at delivering its electrons, but it's pretty darn good.
Is that phi on the bottom?
Yeah, so what we call the flux, and we're not going to start doing physics. Don't flip out on me here, right? So flux is phi. That's our Greek variable for it. All right. So why do we use transformers? I basically say there's two reasons for it. One of them is isolation, and the other one is to scale voltage or current levels. So this is my really crappy model of what a power system looks like, right? And this is maybe becoming a legacy power system to some extent, right? But I have got power plants that step up their voltage to a really high level, right? So they step them up to on the transmission system here. So coming out of a power plant, I might have, I don't know, somewhere in the order of 20-ish kV, kilovolts, okay? Going up onto the transmission level, I might have, could be 130 kV, could be 500 kV, right? I got a couple of options up there. I have really big voltages. And then what I do is I step it down once I get closer. And by the time it gets to your house, it's about 120 volts, much smaller than it ever was, right? So we do all this stepping up of the voltage and then stepping it back down. All right, now, there must be a good reason to do that. What is it?
Lose voltage in distance.
Smaller amounts of current will flow if I step the voltages up really high, okay? And if I have a lot of current, what's the problem with having a lot of current? I'll have a lot of I squared times R in all the resistors. There'll be a lot of power loss, all right? In other words, the Duke wants the power that leaves that power plant to make it to your house, because anything that doesn't make it to your house, they pay for and you don't, right? They still charge you for it somehow, but they would reduce their operating costs if they did, right? Okay. Question, Kojo? You guys have lots of questions here. Yeah.
What you said again? You said that you were talking about when current is high.
Yeah. So let me touch on that point a little bit more about so he was asking about, well, when the voltage is high, the current's low and stuff like. Let me get to that point as I get through the examples here. So I scale those voltages up and down a lot. That's one reason. The other is isolation. Okay. What do I mean by isolation? Well, think about this. These are two separate circuits, right? So I could have a resistor over here, right? Basically, there's a voltage that's created coming out of this coil, right? So if you just take an oscilloscope and you hook up an oscilloscope to the secondary coil with no load, there's a voltage there, even though there is no voltage source, right? Basically, what it's saying is there's a voltage source on the primary, but there's not a voltage source on the secondary. The secondary is acting like a voltage source, okay? So what that means is that I have two circuits and they're isolated from each other, right? They're not connected. There's no current that flows from the primary into the secondary, right? That's really helpful in a lot of cases, all right? That allows us to do a lot of things. That's not as important for you guys here in this class, but we use that property of isolation a lot, that I can have quote unquote two different grounds when I do that, okay?
So basically each winding can be its own independent circuit.
Each winding can be its own independent circuit, yeah. And that is useful for us to be able to do things that way in a lot of cases. All right, we have to do that in a lot of cases. All right. All right, so those are our two reasons for them, and you see them all over the place, right? You go around your neighborhood, you'll see a bunch of them, right? You go outside this building, you'll see a bunch of them, right? They typically have voltage ratings and power ratings, right? We're not talking about, I used the term there a little while ago, 25 kVA. I haven't said what that means yet. We'll talk about that beginning next week. That's a power term. When we talk about, you may have, yeah, but what does it mean? We got to talk about what that means. Okay. So we're going to focus in here on what we call an ideal transformer. All right. A non-ideal transformer would be one where not all of the flux makes it from the primary to the secondary. All right. That's no transformer is perfect. Some of the flux would leak out. In other words, some of the flux would actually go like this and around. Some of it would quote unquote leak and not make it. But if I've, for the most part, if I've designed this guy well, that leakage is usually small. It's usually like 1% of the main flux that goes through the other coil. All right. So essentially what we have is I draw this guy here. This is our circuit model for the ideal transformer. We will only look at these. Key thing is this. When I look at that transformer, there's a couple of things that are denoted there. Okay. There is currents are shown. There's a current I1 and a current I2. Okay. And there's a voltage V1, voltage V2. And there's these dots. All right. So we got to talk about what the dots mean for us. Okay. In looking at this thing, there also has this N1 and N2. What are those numbers here? N1 and N2. Anybody know?
The
Number of
windings of the
turns.
coils.
Number of
Yeah.
coils.
Number of turns, right? So there's N1 turns on the primary, and there's N2 turns on the secondary. Okay. Now, in looking at these are not two inductors staring each other off in a face-off. This thing that you look at right here is called an ideal transformer. That's what it is. Those are not inductors. Okay. Those are elements of the ideal transformer. Ideal transformer, if you think about this thing, it looks like inductors because what I have is a coil of wire, right, around some iron. That's what an inductor is a coil of wire around some iron. There is some inductance to this stuff. We only talk about that when we talk about non-ideal transformers. Okay. And again, most transformers are really, really close to ideal. And so from the perspective of you in 2112, you just need to know the ideal transformer. Okay. But your circuit model for it is that guy. So it's a new element for us. All right. So there's no impedances with it or anything like that. It's just a device that we deal with. And we talk about its voltages and its currents. Okay. So what I want to do is I want to figure out how do I relate the voltages there in that device. Okay. So if the transformer ideal, so basically what I know from physics is that the voltage in a coil is related to the rate of change of flux. That was this goofy equation that I wrote and got rid of because it was too scary looking, right? It was integrals and stuff that nobody really likes to look at. Faraday's law basically says if I talk about what is the voltage here, this voltage, how does that voltage relate to the magnetic field coming out of the coil? So let me look at it specifically from this picture. All right. So there's a magnetic flux in here. And magnetic flux, I said, is how much field. So we usually write that as B times A. All right. The rate of change of flux is the voltage that I get in this thing. So if I looked at, how many turns does this guy have? So look at the picture on the bottom there, right? So it looks like this guy has 1, 2, 3, 4, 5, 6-ish coils. Be careful about how, maybe it's 5, but it looks like it's about 6, okay? How much flux goes through that thing? This guy over here, this secondary coil, how much flux is going through there?
I mean, the amount 6 to permit.
Well, so 6 times the total amount going through that transformer. Because what I have is I have flux going through one coil, and that's the flux phi. And then I have flux going through another coil, and that's the flux phi. And flux going through another coil, and I add those coils all up because they're all connected in series with each other. So if I looked at one coil, I would say the voltage on one coil is basically d phi by dt. And if I put them all in series with each other, right, all of those n coils, I get voltage equals, and I'm gonna call this guy N2, and call this guy N1. Okay, V equals N. So on the secondary sides, this is our secondary here, V2. This is V1. V2 equals N2 d phi 2, like that. All right.
Isn't there supposed to be like a negative in there, like Lenz's law, I think it was called?
All depends. It all depends on how everything is set up. All right. If I have set up my coils the way that I've set up my coils here, then it'll be basically what I have here. All be positives. I'll talk about that in a second because these dots get at your point. Okay. And we don't like having to think about that whole Lenz's law thing, but Lenz's law comes into place when I have to think about where is the flux coming from relative to the way the coil is oriented. We're always going to orient it so there's no negative sign. Okay.
B was the cross-sectional area and A was what? Like for flux? B
A is the cross-sectional area, B is the field, and phi is the total field. So B times A is the total field. And really, it's an integral and all that kind of stuff. But if I simplify the problem, it's B times A. All right. So in coil number 1 and coil number 2, the voltage I have there is N times the rate of change of flux. If I have a changing flux through one turn of coil, I get d phi by dt. If I have 2 turns of coil, I get 2 times that. 3 turns of coil, I get 3 times that. Okay. So on the primary, it would be what, do you think? What would I say for the primary side voltage?
N1.
Yep. N1 times d phi by dt. Now the phi is the same going through that thing. All right. The phi is the same going through that thing. And so if I look at this here, that gives me a way to relate. If I look at these two equations right here.
phi equal to phi negative, right?
Yeah, so the phi is the same, right? So if I look at this right here, I can say that d phi by dt, ooh. If I look at just the first equation, V1 equals N1 times d phi by dt, what is that going to become?
V1 over N1.
Yeah, V1 over N1. If I do it for the other equation,
V2.
V2 over N2, and then we've got our first relationship. Okay. So what it says is that V1 over N1 equals V2 over N2. That's how I can relate these two things. The thing that I always remember about this, and we're going to see this as we go through here, the side with more turns has more voltage. All right. It's always the case that the side with more turns has more voltage. It kind of makes sense. If there's more coils there, I mean, it kind of makes sense. I'm adding up a lot of fluxes through a lot of coils. It's going to have more voltage. All right. The side with more turns has more voltage. Okay. And we'll do an example problem as we go through here. All right. So that's our first relationship. I can relate those. Now, I should also be able to relate the currents there as well. How should I try to relate the currents?
Wouldn't they be inversely proportional?
Yeah.
Well,
And
and why would that be? So current, if voltage goes up, current goes down. So what if you think about what would happen in most circumstances? I'd have a voltage source on one side and a resistor on one side. The way I think of this is in terms of power flow. Where's the power coming from and where's it going in that circuit that I drew right there? Where's the power come from?
from the source.
From the source. And where's it going? To the resistor. So if I think about all the power, there's a power 1 here that enters that primary. And there's a power 2 that leaves that secondary. If this thing is ideal, the power that goes into one must what?
The negative of
Equal
2.
power.
Equal the power coming out. The power coming in must equal the power coming out. So power is what times what?
I times V.
V times I. That's our definition of power, is V times I.
Does power follow the passive?
In a resistor, it becomes I squared R. But the definition of power is V times I. Because of Ohm's law, I can say it's I squared R, but power is V times I, right? So in this case, if the voltage goes up, the current should go down, all right? Which is basically what it means. V times I on one side, V times I on the other side. If voltage is higher, current better be lower, okay? So we can figure that out.
So
All
does
right.
the power of the second winding depend on the power of the first winding?
Yeah, so let me try to walk through that slowly here. So basically, the way that I think about this is I try to relate the primary and the secondary voltage like this. So the basic relationship I have is V1 over N1 equals V2 over N2 like this. All right, that's our key basic relationship. That's the last time we need to talk about physics. Physics got me to that. The rest of it's going to come from circuits. Okay, so this relationship makes a key assumption here. All right. We have these dots. All right, transformer always has these dots. All right. Now, to use a transformer, we always talk about AC voltages, not DC voltages. Why is that?
Because needs a magnetism. Needs a flux. DC has no flux.
DC can have flux.
DC has
DC has flux, but what did I say for Faraday's law to work? Faraday's law said there needs to be a changing field. If I have a DC current flowing in the primary here, there's no changing flux. There's a flux, but it's not a changing flux. I need a changing flux to induce a voltage, right? That's why the power system is AC, right? I need to have this sort of transfer of voltages that happens. It's not going to happen if I had DC sources, right? So, all right. Knowing that, right? Basically, what we do is we say, all right, well, if I put a positive voltage here, so a voltage that looked like this, all right, let's say, so a positive voltage. So in other words, I put the plus sign at the dot. If I had the plus sign at the dot over here, what I would see is a voltage that looked exactly the same. It would be smaller, all right, or bigger, depending on the number of turns, but they would look the same. If I reversed them though, right? So if I had a plus sign here and a minus sign here, what I would get in that case is it would reverse like that.
What's that instantaneous positive terminal do?
What is what?
Isn't that little red dot an instantaneous positive terminal?
No, the red dot is just a red dot. It's just a red dot. The red dot tells me basically whenever my plus sign, it dictates me the polarity of these things. So if I had two coils on top of each other and both the voltages lined up with each other, so they both looked like this, right? If I then switched the leads on my oscilloscope, I would see the polarity of the voltage flip 180 degrees, right? In other words, if I'm measuring, so let's say I put a voltage source plus to minus like this, and I measure plus to minus like this, then I'll see that. If I measured plus to minus like this, okay, so forget that, then this guy would flip over.
So does KVL still apply to each?
Everything applies. KVL, KCL still work. Okay. Nothing has changed about our basic results. So basically, the result of this basically is to say if the plus terminal are both at the dot, then I get this relate. So if they're both at the dot or both not at the dot, then this relationship applies. Okay. So in other words, what I've shown right here, the plus sign is at the dot in both cases. All right. If the plus sign is at the dot in both cases, this relationship up here applies. Okay. If they reverse and one of the plus signs is at the dot and one of them isn't, then I get a negative relationship in the voltages. It's relatively easy to remember. Yeah. Okay. And we'll use it as we go. All right. Now the other idea here is that power is always conserved. All right. Which if power flows into the primary and then out of the secondary, then the two powers, power in has to equal power out, just like KCL, right? Current in equals current out, like that. So given the way that I've written this guy right here, the way that I'll do this with the currents shown going in, what I'll say is that power 1, which is V1 I1, and power 2 is V2 I2. And we're going to say a lot more about power next week. Okay. What can I say about those two things here? Well, I can say that power 1 plus power 2 has to be equal to 0, right? The total power into that thing has to be 0, because otherwise there would be power being created. All right, so power 1 plus power 2 has to equal 0. So what I would say here is that, well, given the way these guys are set up, I have V1 I1 plus V2 I2 equals 0. So given our relationship here, given the way these guys are set up, I have V1 over N1 equals V2 over N2, like that. Okay. So what should I do to help me out here? If I want to figure out the relationship between the currents, what should I do next? Well, so basically, let's plug in that V1 equals N1 over N2 times V2, right? So what I'll say is that I get N1 over N2 times V2 times I1 plus V2 I2 equals 0, like that. How can I simplify that expression right there? I have a V2 in both of those terms, right? They cancel because that whole thing's equal to 0. And I can say that I2 equals negative I1 times N1 over N2, yeah. Okay. All right. So what that basically says is if I had 4 volts here, all right, so let's say let me go to, if I go here, if I have an example here, I got 4 turns and 1 turn like that, okay? If I have an example like that, what it says is the magnitude of the current on the primary side, so let's do this example, V1 over 4 equals V2 over 1, right? What that says is that V1 is 4 times V2, okay? Thinking about that power relationship, what that ultimately means is that I1 is going to be 1/4 of I2. All right, and I can plug that into the relationships that I have right there, right? But basically, if you think about it, the current on the primary or the voltage on the primary is 4 times bigger than the secondary. The current on the primary is going to be 4 times smaller than the current on the secondary, right? So what I always do, and that's why I always try to remember it, the side with more turns always has more voltage. The side with fewer turns always has more current. That's my way of checking myself to see that I actually did it right. All right. This would better be the case that the side with more voltage has more turns. Side with fewer turns has more current. Okay. All right. Let me see here. Check some. There's a point I was trying to make. All right. Yeah. Okay. Yeah, I made my point. Okay. So the way that I always think about this is really in terms of those things. I have sort of a process that I think through with this stuff. So we're going to look at an example circuit and try to apply this, right? But what I do is I write the voltage relationship. I write the power relationship based on the currents and the voltages. And then I figure out the current relationship from the power relationship. I don't like to memorize things. All right. So I can remember the voltage relationship. V1 over N1 equals V2 over N2. All right. That's the only thing I remember. Then I remember the powers. All right. And then once I go through those 3 steps, then I get my circuit relationships using those results. Okay. So the example we're going to look at is this guy. All right. And what I want to do is I want to solve for the phasors V1 and V2 and I1 and I2. Okay. Now, what's a good way to do this? Any thoughts as to how I would try to solve this problem?
Would you want to combine impedance?
So what'd you say, Anthony?
I was just saying, to add R1 with L, kind of get impedance together.
Yeah, well, can I get my pieces together? So basically this guy's going to be a circuit with phasors, all my typical phasor stuff. I would think that this is basically, if this is 2 meshes. That's what this is. Right? There's a mesh on the primary side, and there's a mesh on the secondary side.
But are we viewing this as just one circuit?
So it's one circuit, but basically there's 2 meshes. There's no current that moves between the 2 sides, right? What I'm going to say is I got a mesh current over here, I1, and I got a mesh current over here, I2, like that. And what I'm going to do is I'm going to solve those 2 things and use my relationships for the voltages and the currents. Okay. Yeah, well, so is the negative, so the question he asks is the negative J24 here in series with the 32 and the 16? Yeah. And how do I know they're in series? Because
KVL.
Share the same current.
same current, right? So if I look at this, what's going to happen is I1 is going to flow into the primary and then back out. All right, so I can think of basically the secondary and the primary as 2 different loops here, okay? So I want to go through my steps here. I want to write the voltage relationship, write the power relationship, get the current relationship from that, okay? And then figure out how I can set up circuit equations, KVL equations, to do my mesh analysis. Okay, that's what we're going to do. All right, so here, given the way the voltages are set up, and I will always make sure that you get it this way, there is a plus sign at the dot in both cases. Okay, so with a plus sign at the dot in both cases, what do I know is true about my voltages here? V1 over N1, so V1 over 4 in this case, equals V2 over 1, or just simply V2.
Oh, that's that 4-1.
Yeah. Okay. So the 4-to-1, this guy is what I call sort of my turns ratio. You would never have a transformer with 4 turns and 1 turn. Most likely it's 250 and 1,000 or something like that. All right. But it's a ratio of turns. Okay. So in this case, there's 4 times the number of turns on the primary as there are in the secondary. So there's more voltage over there. Okay. We've already got that. V1 has 4 times V2. Okay. So that's step 1. It's that straightforward for this. Okay. How do I write the power here? All right. How do I write the power here? So I have P1 is V1 I1. So power is going in to the plus terminal. All right. It's going into the dot. Now, what about on the secondary side? We look at where's the current going. Is the current going into the dot or out of the dot? It's going into the dot. I2 would go around and into the dot. So I would say V2, I2, like that. All right, so we look at, when we write the power relationship, I look at, is it going into the dot or is it going out of the dot? In this case, it's going into the dot, just like I had in my setup there. All right, so when it's going into the dot like that, I get what I show here. All right, and so the way that I write this, the way I always set this up is I basically say P1 plus P2 equals 0, right? Or V1 I1 plus V2 I2 equals 0 like that.
Do transformers only work with two windings, or could you have a transformer?
I can have a whole ton of windings, yeah.
Okay,
That's always possible.
so summation of all the power of all the windings. Is always
It would be, yeah, but we're not gonna deal with problems like that here. You could, in fact, there's three-phase transformers. You get those all the time, but we're not gonna touch that. All right. So what do I want to do? My third step was to figure out the current relationship. Okay. So let's look at what we knew. Well, we knew from here that V2 equals V1 over 4, right? So I basically have V2 equals V1 over 4, like that. I also have V1 I1 plus V2 I2 equals 0. One of the things people like when we get into power, I think, and transformers and all that stuff, is we usually don't have like weird loops with dependent sources going this way and that way. Usually they get much simpler. It's usually 2 loops, and they're usually simpler circuits. Okay. And this is a relatively simple circuit. There's just 2 meshes to deal with. Okay. I want to get the current relationship in this step. So what should I do?
I plug V2 in.
Yep, plug V2 in. So I basically have V1 I1 plus V1 over 4 was I2 equals 0, right? So the V1s cancel out, and I get that I1 equals negative I2 over 4, right? So I have V1, I guess I'll write it this way, V1 equals 4 V2. And again, it all assumes the polarities that I've got written right here. The reason I like to do this is you look in the textbook, sometimes they'll give you like 8 different versions of these relationships. I just think of it in terms of, if I write my powers as in this way, power 1 plus power 2 equals 0, and that I look very carefully, is the current going into the dot or out of the dot. All right, we got more examples that we'll do Monday where they're weirder, right, where it's out of the dot and stuff like that, right? So I have V1 equals 4 V2, and I have I2 equals negative 4 I1. Right, those are my 2 relationships in this case. Okay. All right, so what should I do next? Now it's time to do circuit analysis. Okay. Now it's time to do circuit analysis. So what should I do to do circuit analysis here?
I'm guessing we're starting to bring flux into the equation.
Play a 2 loop before.
Solving for, by the way.
So we do mesh, right? So how would I do that here? Well, so I'd solve for the mesh currents. Once I have the mesh currents, I can solve for whatever I want to. Right? I can solve for the voltages on the transformer and all that stuff. So this case, what I'm going to say is, how do I do mesh in this case? So let me write up here, V2 equals V1 over 4, and I1 equals negative I2 over 4. Okay, those are our key relationships. Okay, so how do I do mesh in this case? Well, I got to write, so I1 and I2 define my mesh current. So here's I1, here's I2, like that. Okay, so when I do mesh, very first thing I do is mark out the polarities here of everything, like that. And then over here, I'm going to do like this, okay? All right, so let's do my KVL. So let's do the primary loop, okay? So I'm going to start in the bottom corner. So I'm going to say 0 equals, then what? How do I write my KVL from there?
Negative 100.
Negative 100. Now I could say negative 100 angle 0, but I don't have to say angle in this case, right? Because the angle is 0. Okay, so negative 100. And then I say plus J, I'm going to do it this way, plus I1 times what?
32 plus J.
32 plus J16, like that, right? Then what? Well, the next thing I hit is that primary. Okay. That's V1. Right? That's just the voltage across there, V1. Okay.
You just put, oh, never mind.
Well, so if I wanted, so just bear in mind, if I'm going to solve for the two mesh currents, I'm going to solve for I1 and I2. So I'm going to have to get two equations in terms of I1 and I2, and only I1 and I2. Okay. So I've gotten there so far. Then what? I got one more thing left in that loop, right?
Capacitor.
Capacitor, right? So plus the voltage across that capacitor, which is plus I1 times negative J24. All right, and I didn't put the negative in the front. I didn't do it on purpose because I know it's plus, because it's plus the minus in my KVL, right? So I like saying I go plus whatever my Ohm's law tells me for that device, right? All right, so that guy's got two things that I don't know, right? V1 and I1. All right, so that's I got issues potentially. All right, so that's my primary loop. What's my secondary loop? So again, I'm going to start in the corner. I'm going to go around in a counterclockwise way, or sorry, clockwise way. All right, so I go through V2 first. I go through that secondary coil first. So when I go through that secondary coil, what am I doing? I'm going from plus to minus on V2. So what do I write first?
V2.
V2. And then I go through a series combination of impedances. So I have I2. And what do I multiply that by?
Times 3 plus 2J.
Yep, 3 plus J2. And then I say, I go plus the minus on this 20 angle negative 20 voltage source. Okay. Now, in this case, now I've got what? I've got a whole bunch of different variables, don't I? Right? So now I've got 4 variables and 2 equations, but I actually have another 2 equations that I can use, right? That come from the transformer relationship. Okay. So what I'm going to do over here is I'm going to say, well, I'm going to rearrange this guy and say V2 equals what? Well, let's move the V2 over here. And once I got V2 equals negative I2 times 3 plus J2 minus 20 angle negative 20, like that. Okay. So when I look at that whole thing right there, right, I can make I can use my relationships a little bit. So when I look at that bottom picture right here, I see that this guy right here, V2 is equal to this whole thing. Okay. V2 is equal to that whole thing. Well, can't I get rid of I2 in that equation?
Yeah, with the I1.
Basically, I can get rid of I2 by saying I2 equals negative 4I1, right? So this guy becomes here 4I1 times 3 plus J2 minus 20 angle negative 20. Follow what I did? Right? I used my current relationship, substituted it in there. Now, what else do I know about V2? Well, V2 is not in my other equation right here. So I've reduced the number of variables here, right? So now what do I have? I have V2, I1, and V1. Can I get rid of V2 as well? What is V? What is? Yep, V2 equals V1 over 4, right? V2 equals V1 over 4. So what I can say is, if I take that last relationship, V2 equals 4I1, what was it? Times 3 plus J2 minus 20 angle negative 20, like that. Make sure that's right. Yep. Okay. This is my V2. I know that V2 is equal to V1 over 4, right? So I can say that this guy, how can I use that here? Well, I can say that V1 is equal to what? How can I use these? How can I combine these? Yep. Yep, 4 times that. So it would become 16I1 times 3 plus J2 minus 80 angle negative 20. All right. Now that's one equation, and this is one equation up here. So the primary loop was giving me an equation. The primary loop gave me this equation: 0 equals negative 100. Oops. Negative 100 plus I1 times 32 plus J16. Oops. Plus V1 minus J24 times I1, like that. So what would I do?
Make V1 equal to V1.
Make V1 equal to that, and I've got one term, right? So I would solve for I1. At that point, it's pretty easy to solve for I2, because I2 is related through this guy right here, right? So it's pretty straightforward. This is a trickier circuit than a lot of them would be. So oftentimes I just have an impedance over on the secondary. In this case, I got sources on both sides, right? So this is a trickier type of problem that you would have with the transformer.
Can I ask a design question that probably doesn't have to do with what
In a second, yeah. Let me finish. Okay. So I'm kind of done, but I want to make sure. So you guys follow that process, right? So we're going to do more examples Monday, right? So Monday's, kind of more examples on this transformer idea. And then we're going to start basically saying, okay, well, let's put this guy into a quote unquote power system where we have power in an AC sense. So power in DC was easy. All you had was resistors. Now we got capacitors and inductors. Resistors eat power. They eat energy, right? They basically consume energy. Inductors and capacitors store it. That's different. So the whole power thing becomes completely different when I talk about AC stuff. All right, so we'll talk about that more beginning on Wednesday. Okay. All right. Any questions?
Yeah, real quick, I think I missed it, but the relationship between 16I1, you used V2, right?
Yeah.
Okay.
Yep, that's right. Basically I plugged in this guy. So I'll post this and you can kind of watch that slowly.
Okay, thanks.
Yeah.